Hi, and welcome to another Hopper language video. This is sort of a mix of a language video, a tutorial video, and a sort of Hopper microcontrollers video. It's on the Raspberry Pi Pico. And it's a tutorial in that it's going to be slightly longer form than usual. I think occasionally it's worth having some long tutorials. There'll be links in the description at the end to the source code from the completed source code at the end of this example. And there'll also be links at the end of the video to other playlists and getting started. So if you don't know what Hopper is, it's a modern semicolon and curly brace language that's very similar to Java or C#, but designed to run on small devices. For example, it runs on 8-bit 6502s, but also on microcontrollers like the Raspberry Pi Pico. Anyway, I've got an example to cut and paste in here, so the typing is going to be fast. But like I said, the source code will be at the end. So this is what a typical Hopper program looks like. Starts with the word program. It's very Pascal-like that, because there's programs and units. This is your main. It doesn't have a name because it's always the same. It's always main. And then for the microcontrollers, you got to put in a define to say which microcontroller you're using. If you don't do that and you try and compile, at the bottom of the screen you'll get an error here saying, if you double click on the error, it'll take you to the location of the issue, and to use MCU unit, you need to have a board defined, and these are the most common ones and the pros and cons and all that. Yeah. So let's go back and put that in. So it'll tell you when you're missing things. And if you use the MCU unit, then you can use pretty much all the language features that are available on the microcontrollers get included for you in a way that makes sense. So this tutorial, as per the title, is about timers. So to set up a timer in Hopper, I'm going to use these. I'm going to use these LEDs down here to illustrate what I'm doing. So I've got, let's just set those up quickly. So they're on GPIO pins 16 and 17. And I'm going to have an alarm LED and a timer LED. And then to initialize them, looks very Arduino-esque, this, setting the pin mode to output of both of them, the alarm pin and the timer pin, and then setting them to false to turn them off. And then the built-in LED is even easier than that. If you can just turn the built-in LED off just by going LED off like that. Okay, so we've got our LEDs set up to do nothing right now. And then we're going to have a main program loop at the bottom here that's just going to keep going forever. Doesn't have to do anything. And then to use a timer, they're events, and events in in Hopper, you use a function pointer or a callback is a delegate, and that's taken from C#. That's where I came up, with that. So we're going to have a timer callback, and we're going to initialize it. Let's just leave it like that for now. So I've created a callback pointer, a delegate, and now to initialize it, I'm going to want to set it to let's just name it a delegate so we know what it is. Okay, and then I'm going to initialize it to point to a function, a method that's going to handle the callbacks for this timer, and that's going to be called my timer callback. I'm also going to want to have an ID. I'm going to do the same and make that a global as well, like a local variable ID. I don't know how I can do this in one line, but for the reasons of my example, I'll do it in two. And then to initialize the timer, I do timer start, the amount of milliseconds, and this is a repeating timer, so every 2000 milliseconds it's going to call my timer delegate. And to see when that's all defined, if you go into this MCU unit, you'll see it includes a timer unit, and inside there you can see you can start timers and start alarms. I'll come back to that later. So now we're going to start our timer, And then it's going to go around in circles and do things. But right now it's going to tell me I don't have a timer callback function if I build. So if I say build, which is F7 shortcut key, error timeback, so if I double click on the error, it says this doesn't exist. Right, that's quite true. I didn't make myself a callback function. So there's my callback function. So if I do that, it should complain again. Timer callback, no matching overload found. Yes, because that's not the correct signature for the callback. Because in order for you to be able to use the same callback with multiple different timers, it'll pass in the timer ID. So this timer ID gets passed in. So now it should happen. So now that's a finished program, and I could actually run it. So if I build that and I upload it to my device, probably to my device on. Let's say retry with my serial port. There we go. It had a problem connecting with my serial port for some reason. Now I've uploaded it at the bottom of the screen. If the title went to green, so we're in the debugger. The debugger says uploaded this. So I'm ready to run. So if I F5 to run, let's see what happens. It's running in the debugger, and it's doing gloriously doing nothing. Yeah. Let's just put that back in the middle of the video there. So I'll Control C out of that. So we want to see that something's happening. So how's about we turn one of our pins on at the beginning of it and then turn it off at the end, right? Let's do that. And you know that's not going to work either yet, right? So if I F5 that, run it again, it's running again. And it still looks like nothing's happening, right? Why? So we stop in there. How about we let it take a little time with the pin? Now we get a half a second of, that looked like more than half a second, but it's supposedly just a half a second. There we go. Half a second every 2 seconds. And this brings me to an interesting point. This is, in Arduino, this would be an interrupt service routine. And inside an interrupt service routine, you shouldn't do things like call delay. You shouldn't do slow running stuff. And you shouldn't print to the serial port. But this is not Arduino, so we can do more interesting things. Let's count every time we hit that timer, and we'll increment the counter, and we could put it out to the serial port, like I was saying. So this right here. If I'm running on the MCU, it's going to write it to the serial port. And it's going to say timer, my timer ID, which is this here, toString, a colon, the count, which is that count, and then milliseconds minus start. So I want to have it know when the start time was. So millis works in longs. So we should probably set that just before we start the timer. Then we can see how accurate the timer is over there. Yeah, that'll work. And what else do we want to do? Yeah, okay. So this write doesn't put a new line. So once we're finished with the writing, we can that'll put it done after the 500 has passed. So let's build that again. And all the shortcut keys are on the menu here. So the keys I'm using right now. So I'm going, launch debugger, F5, and then let's just run that in the debugger. And now we've got some stuff happening on the screen. Not ideal. Let's stop that again. So I've got a reset button on my Arduino, very handy. Serial lost, let's run that again. Let's do the reset and launch this. There we go. Don't know what went wrong there. But you have a debugger and you can find out. So let's run it again. There we go, that's better. Timers are tricky. So if you break right now, the time, so this will keep going forever. And we can see that the increment, it's exactly 2000 milliseconds between them, and it took like 1 millisecond to set up. So we lost that 1 millisecond at the beginning. So but the repeat is every 2000 milliseconds. Events are pretty tricky, especially ones that are hooked to a timer. So if I Control C out of this, and then I continue running by press. So I've broken into the debugger, right? And then I continue running. It's caught up on all those timer events. So, and there was a longer break in between them too. So it didn't stop generating events when I Control-C'd out of it. And my plan actually is to stop that from happening, so that if you Control-C out of this, if you stop the program and reload, you should have nothing left in the in that buffer there. It should start from scratch again. There shouldn't be any stray events. Stopping the program should kill all the events. All right, so that's a simple timer event, and we're keeping that light on for. We're staying in this loop for half a second, which you wouldn't want to do in an interrupt service routine in Arduino, but here it's not an interrupt service routine, it's an event handler. Okay, so interrupts are queued up into events, so that's how it's implemented. All right, let's carry on with our demo. So let's put a faster one onto the built-in LED. So we'll put that onto the built-in LED, and this built-in LED I can just alternate like that, so I can flick it on and off. And we've already set it to start with false, and we can just put that in here before we implement the other one. So our timer delegate is fast, and we're going to start the timer ID with this one. This is going to be every 100 milliseconds. Let's go with that. And let's run that. So now we can see our the purpose of this demo was to show that these interrupts can interrupt each other. So also, unlike interrupt service routines on an Arduino, where interrupts are disabled during an during an interrupt service routine, these are events. So the events can interrupt each other, and they can stall each other, as this 500 millisecond event is stalling the 100 millisecond event every time it happens. But it is interesting to note that the 500 one, which is the longer time, is still very, very accurate. All right. So next part of the demo. How do we stop an event? So we've a timer, a repeating timer. So we've already got a count here. So inside our loop, we should keep track of whether we've already stopped it. So we want to have it cancelled. And another thing about Hopper, everything is zero initialized by default. So the timer count is zero initialized, start is zero initialized, cancelled is zero initialized, and the zero value is false. So I don't need to initialize things. Also something we inherited from C#. So now, if the timer count is 10, and we haven't cancelled yet, then we're going to stop the timer based on the ID. The last ID was from this one, so it's going to be the 2000 millisecond one that's going to get stopped, and then we're going to stop the timer. And the other one should carry on, so let's build that. And let's run that. Run it again. See, that's not very pretty. There was some stray stuff in our, it didn't reset our timer, so let's stop that. Try restarting again. There we go, that's better. Still have some cleanup to do. So we're still getting interrupted every 500 milliseconds. Our fast timer is being interrupted by our slow one. But we'll see what happens when we get to 10. It stopped it, so now there's no interruption. So the 2000 millisecond one has stopped happening. All right, so that's about as much as we can say about repeating timers. So the next thing to move on to is one-shot timers, or what we call alarms. Well, on the Raspberry Pi Pico, they're called alarm. This is implemented over the Raspberry Pi Pico SDK. So let's have a look. Let's make ourselves an alarm. So I'm gonna have an alarm callback that's very similar to my timer callback. Let's pop that in here. So, but instead of getting a timer ID, it gets an alarm ID. They're the same idea. They're a uint. Which brings me to how many of these things can you have? Well, inside the firmware, I've limited it to 16, and 0 means it failed to initialize. So if the start returns 0, it means it failed to initialize, because these are unsigned integers. 0 seemed a good failure number. So the actual valid timers are 1 through 16 right now, but there's no reason to limit to 16. If for some reason you need lots of long timers, you could increase the, rebuild the firmware and have a bigger number. Having lots of shorter timers, eventually, there's not that much processing power on this thing. Eventually it'll stomp on itself, so you have to be aware of that. So we've got an alarm pin too. That's the other pin, the one that's orange out in that video. And I've got similar stuff here. So let's do that for now. So this is going to be, it's going to light up that pin for 1 second when the alarm triggers, right? Now we need to go and hook up a event handler for it. So let's do that. So it's the same kind of interrupt service delegate, so we can reuse this delegate argument here, delegate variable. So we just do that. So we hook, I could do this in one line by just putting that in there, but this is sort of like, that's your delegate, pass it off. And I'm setting an alarm to go off in 10 seconds. No. So that's, it's 10 seconds, which is 5 times those. That looks like a good idea. Okay. So I had a typo in my example. So let's do that. I think that's everything done. Build it. And let's upload it. And start it. Not a lot happening. Let's Control C out of that. Some reason it's hung. Let's try that again. This is still quite new. I haven't made it super stable yet. There we go. So it's got an alarm. We've got an alarm set up for 10 seconds, and there we go. So we're at 6 seconds. Watch what happens with the lights when we hit 10 seconds. See the orange one lit up there briefly. And the orange one, in addition to interrupting the fast timer, also it was called. It also interrupted the 2-second timer. Anyway, so that was the one shot that happened, the 10-second alarm. I'll just break out of this, reload, and run again. So we got an alarm set for 10 seconds. So let's watch again what happens at 10 seconds. So we're getting our 2 second. There's our 8. Watch the 10. There we go. It's lit up. And it lit up both LEDs at the same time, which means that event interrupted both the other events. And there's a reason for that. If you have a look, it doesn't take much to figure it out. This one's pretty short. It's every 100 mils. This one's every 500 mils. This one's every 1,000 mil. So it's going to overlap. Well, the start times are synchronized, because this one's 10 seconds and this one's also going to hit on 10 seconds. So this one's going to overlap that one. And this one's multiples of 100 mils, so it's also going to hit on 10 seconds. So at that same time, this one was the last one created. So by a small fraction of it's like equal twins are not quite equal. It's going to interrupt the other two. Okay, I have one more thing to demonstrate with alarms and just like you can stop a timer, you can cancel an alarm. So let's make ourselves an alarm to cancel. So we need to have a global variable so we can get to it from the callback. And then when we're going to cancel the alarm from within the other alarm. Again, something you wouldn't be able to do in Arduino. I shudder to think what would try to happen if you did that inside an interrupt service routine. So we're going to cancel this alarm when the 10-second alarm gets called. We're going to cancel our 20-second alarm. And now let's make ourselves a 20-second or 15-second alarm, or just anything longer than 10 seconds, really. So let's create that. So yeah, 15-second alarm hooked up. And it should get cancelled by the other alarm. So when the 10-second alarm goes off, it should cancel the 15-second alarm. Let's build that. Upload. and run. I've got the same problem again. Fortunately, it's not a big drama to fix it right now for my demo, but I obviously need to solve that. Let's try again. So we're running, so we set up 2 alarms, we set up 2 timers, and we're off to the races. So during our alarm, we cancelled the 2-second alarm. That's what happened there. The 15-second alarm, that means we shouldn't see a 15-second alarm here, and we don't. We went from 14 to 16 seconds without setting an alarm. Okay. Let's go have a look at a few more things about this before I wrap it up. I wonder if I can do full screen here. Yeah, let's do that. Let's fade to that. That's better. Okay. So, because I want to pull up a calculator as well. Let's do that. Okay. So if we go and look at the timer unit, there's 2 versions of start and 2 versions of alarm, and one takes a uint and the other takes a long. And it'll automatically, because Hopper supports overloaded methods, so if you pass in a long, it'll call the correct one. But they're both milliseconds, and the reason is because if you limit yourself to uints, which the maximum is FFFF, which means 65 seconds is your longest time you can set for a one-shot or for a recurring time. Whereas if you pass in a long, you get that really divided by 2 because it's signed. And then if we, kind of a big number to look at, so if we divide that by milliseconds, so now our timers can can reach up to about just over 2 million seconds. So divided by 60, 35,000 minutes divided by 60, 596 hours. Oh, that didn't work so well. 596. I switched it. 596 divided by 24. Is that right? 24 days. Let's try that again. So 1, 2, 3, 4. 1, 2, 3, 4 divided by 2. Yeah. And now we switch to decimal. Divide by 1,000. That many seconds divided by 3600. Oh, yeah, that many hours. So divided by 24. It's 24 days. So that's a ridiculously long time to have a one-shot timer run, because it ain't going to be that accurate. But anyway, these things should be flexible enough so that it serves the purposes of most of what we're trying to do with this platform. Anyhow, thank you for watching. Let's just restart this guy again. The reset button. There we go. That little flicker is to show that it started, and then I'll fade out. I look forward to your comments to the video and your feedback.